Okay, on number 36, they ask how far does a wave travel in one period? Well, as I said in class, one period and one wavelength are really closely related. Those are the two things that happen in one vibration of the source. So as the source, say we were looking at a simple harmonic oscillator and say it was vibrating up and down like this, maybe it's the wave is traveling out from that source and it's doing this kind of thing right here. Well, in one period, that is the time that it took to go maybe from there all the way down and all the way back, this much wave was produced. And so that was one wavelength of wave was produced. Number 37 says a wave oscillates 4 times a second and it has a wavelength of 3 meters. What's the frequency? Well, the 4 times per second is the frequency. Remember, the frequency is the number of repetitions, the number of cycles, the number of oscillations you have in a given time interval. And so that frequency is going to be 4 hertz. The period is the reciprocal of that. And so I can just simply take the reciprocal of the 4 hertz and make that 1 over 4. Unit is 1 over 4 and 1 over second, and so that's going to be 0.25 seconds. I can also think of that conceptually too, because a period is how long it takes for one oscillation to happen. If 4 of them are happening in a second, then it's taking 1/4 of a second for each oscillation to happen. And then the speed of the wave, as we know, the speed of the wave is equal to the wavelength times the frequency. And so I can take the wavelength of 3 meters and multiply by the frequency of 4 hertz, and I can get 12 meters a second. On number 38, it says you produce a wave by oscillating the end of a rope up and down 2 times a second. What's the frequency? Well, that is the frequency. 2 times per second is 2 hertz. What's the period? Remember, that's the time for each oscillation to happen. And so if you're doing it 2 times a second, so each one is taking 1/2 of a second. That's also the reciprocal of the 2 hertz. And if the wave travels with a speed of 5 meters per second, what's the wavelength? Well, we know that wave speed is wavelength times frequency. And so the wavelength is the wave speed divided by the frequency. And so I can take that 5 meters per second and I can divide by the frequency of 2 hertz. And I can get a wavelength of 2.5 meters. On number 43, it says you sit in a fishing boat and you notice that 12 waves pass the boat every 45 seconds. And so 12 waves every 45 seconds is a way for them to tell you the period and frequency. If I wanted the frequency, I can take that number of oscillations and divide by the time that took to happen. Notice I write it out as time and not just a capital T, because that's not necessarily the period. It's just a corresponding number of oscillations and a corresponding amount of time. And so I'm going to say that there are 12 oscillations, 12 waves pass in 45 seconds. And so that gives me 0.2667 hertz for the frequency. Now, they say the distance from one crest to the next is 7.5 meters. And so that is the wavelength is 7.5 meters. And they want the speed of the wave. And so the wave speed is the wavelength times the frequency. And so if I multiply that wavelength and that frequency together, I get 2 meters per second. On number 44, it says a wave moves by you with a speed of 5.6 meters per second. Distance from the crest of this wave to the next trough is 2.4 meters. What's the frequency of the wave? This time they're not telling you the wavelength directly. They're telling it to you in a strange kind of way. They're saying that from the crest to the next trough, that's 2.4 meters. we know that the wavelength is a full wave shape, and so the wavelength here is going to be 4.8 meters. Wave speed is wavelength times frequency, so frequency is wave speed divided by wavelength. So I'll take that 5.6 meters per second and I'll divide by the 4.8 meters. And that's going to give me 1.1667 1/seconds, or hertz. Significant figures wise, we'll make that 1.2 hertz. '86 is a nice one. '86 is showing 3 waves like you have a photograph of the wave. And so they put them on the XY axis, but realize what you're looking at there. This is y as a function of x and not y as a function of t like we're going to see in the next example. So they say all of the waves are moving with the same wave speed, which would make a lot of sense. Maybe there are 3 waves that are in the same medium, same spring, same puddle of water, whatever. If it's in the same medium, everything else being the same, it's going to travel at the same speed. And so this one, A, is, well, to be made this way, it's going to have a really high frequency of the vibrating source, whereas B was a lower frequency, and that is they were making disturbances less often, and C is in between. And so they're saying rank them in terms of increasing frequency, and so B is the one that is made least often, C is in between, and A is made most often. And so we have that as our order for the increasing order of the frequency. For the wavelength, I think that's actually pretty easy to see. You can look at the wavelength here. The wavelength on B is super long, and so we have this giant wavelength. On C, it's much smaller, and on A, look, that's really small. So we've got that little baby wavelength. And so for increasing wavelength, I have A, and then C, and then B. And A is the smallest, and C is in the middle, and B is the greatest. We're not surprised to see this, by the way, because if they're all moving at the same speed, then the one that has the smallest wavelength is going to have the greatest frequency, medium, and smallest frequency and biggest wavelength. On number 108, we have a different kind of scenario, very different actually. This one's more about just a vibration than a wave. Although when you look at the picture, it looks very wave-like. But this picture is a graph of displacement versus time. So we have a simple harmonic oscillator. It's a mass on a spring. Remember, this is where we very first started. We had a spring with a mass that could alternate one amplitude this way, one amplitude that way. And so this graph is showing you where the mass is as a function of time. At the very beginning, they started the timing at when the thing was right in the middle and going over to the right. And so in a quarter of a period, it was all the way out to this maximum amplitude. And then in another quarter of a period, it was back to the center. And then in another of a quarter of a period, it was over at this maximum negative amplitude. And then in another quarter of a period, it was over at the center. And so in one vibration, and over and back and over and back, it took 4 seconds for that to happen. So period of the motion here is 4 seconds. And then part B, what's the amplitude of the motion? Well, you can see that it's moving 0.5 meters each way. And so that's our amplitude of the motion. Our amplitude is 0.5. Remember, the amplitude is a scalar, and so you leave the positive or negative off. Sometimes it's going to have this, it's going to go to the right, and you're going to see a positive 0.5 like I'm showing here. Sometimes it's going to go over to the left, and you're going to see a negative 0.5. Now they want us to calculate the spring constant. Remember, all of this is related in that equation where the period of a simple harmonic oscillator is 2 pi square root of the mass of the oscillator divided by the spring constant. And so if I want that spring constant, rather than just substituting in numbers, I think I'm going to square everything. Period square is 4 pi square m over k. And now I'll multiply both sides by k, and I will divide both sides by that period squared. So putting in a 3.8 kilograms for the mass and a period of 4 seconds, you're going to get a K value of 9.4 newtons per meter.